oh, here we go, equals AX. So let lambda 1 be an eigenvalue of A. So here we have this linearization. So this is that Jacobian that we just had a minute ago at the bottom down here. We'll call it A. Let lambda 1 be an eigenvalue of A if the real part of lambda I is less than 0 for all I equals 1 to n, then the equilibrium point x equals 0 of x dot equals f of x is locally exponentially stable. There is a rigorous definition of what exponential stability is. But for what we're doing here today, just know that it is has properties like asymptotic stability. It'll be stable and attractive, but there's also some additional conditions besides that it also meets, so it's kind of a more stringent version of asymptotic stability in some sense. Like it's a type of asymptotic stability with additional conditions. So things that are exponentially stable are asymptotically stable, but not the other way around necessarily. Okay.
Can you show this in a graph or in a plot?
The thing about exponentially stable, the difference is something about like, this is, I don't quite remember, that's why I'm hesitant to exactly comment, but it's not really a difference in, like qualitatively, if you were to say, oh, what's happening when it's exponentially stable, then the state is going to the origin over time. But it's some special like technical difference in like the way the trajectory behaves or something about, I'll say what I believe it is, but then you can check in the Khalil upstairs if you like. But I would have to look at the book because I don't know exactly. So this tells something that you can get from your linearization. So this is again a local result, but it means that if you can get your origin and then you can get a linearization, and if you see all your eigenvalues are negative, then you can say that the origin is locally exponentially stable. So it is actually possible. So this kind of expands our toolbox of what we can do. So last time we started going through some definitions of different stability types, but we were using that epsilon delta stuff that seems kind of hard to really use very well, like to look at an equilibrium point, and then to say, well, based on epsilon delta, like you kind of can for some, but in general, it's kind of hard. But this one is, I think more, oh, this should probably be then. The equilibrium. So, yeah, but then this one is fairly easy to use because we can take the linearization of any dimensional system, nonlinear system, and then try to apply this. And if we can, then we can tell something about a local stability result. And then, so you, if your eigenvalue of any of them was positive, then you could say that the origin of the nonlinear system was unstable. But if there's 0 eigenvalues, now you're going to just conclude that you can't tell from the linearization alone. So, now, the moment we've been waiting for! Lyapunov stability! Yeah! The whole point of this entire class was to talk about So I'm trying to think the best way to do this. I think I want to give the kind of the abstract, the abstract and like really brilliant idea of Lyapunov stability, and then I'll go through this example. The reason I'm not going to go through this example first is because it confused me when I first learned it, because I thought it was telling me that I had to find like functions of a specific type, and it wasn't. So I'm going to talk abstract, then I'll give an example that kind of shows this, even though the whole thing about Lyapunov stability is abstract. So if you imagine, here's the origin. I can have what's called a Lyapunov function. So we'll call it v of x. So here's a function called a Lyapunov function. So then you say, what is a Lyapunov function? It's a function that has some properties. If you remember, like how similar in concept to the idea that like a norm, for example, is sort of like a function that has certain properties, like, oh, when you take the norm of this vector, it's greater than or equal to 0, etc. So here we're learning about a new function that we're going to denote v of x, and it's going to be some function that you find that has certain special properties. One of these is that v of x, I'll make this a dot so it doesn't get confused with a negative. So v of x is greater than 0 for all x contained in some domain that you're looking at, but not including 0. So this means the domain, but not 0. We also require v of x equals 0 if x is equal to 0. And so now this is really, really amazing. So, have I told you about this much before, Enrique? It's so exciting. I'm going to show Kim for the first time. Okay. So, if you have this function is 0 at 0. If you take its value somewhere else, and if you happen to know, say that I have this region here. If everywhere in this region, so here's the origin. Here's an initial point. If everywhere in, let's call this, I'm going to call this D for a minute. We may find out that that's not the best term for it in a minute. That's fine, just to make this sort of abstract point. If everywhere in D, v dot is less than 0, so this is dv dt equals dv dx dx dt, because it's because v is a function of x. And so let me just first describe what is this trying to tell you. So this is saying, say you have x dot equals x squared, and then that I have v of x is also equal to x squared. So then v dot is equal to, so dv dx would be 2x,
Right.
And then dx dt is x dot, because that's dx dt. So this is 2x, and now I plug in this x dot up here, times x squared equals 2x cubed. So that's sort of an example of what this is saying. And so what this sort of is saying is you're getting the way that v is changing along the trajectory of x. So that you want to know, if I start here and then you have an initial condition for a differential equation. So regardless of what your V is, like you don't need V to numerically integrate a differential equation. When you solve a differential equation, you solve for the trajectory. What you need is an initial condition. So you give an initial condition, say it's here. The closed loop, or not closed loop, just the state of the system, we just have it x dot equals f of x, will evolve in some way based on your initial condition. Now we start saying, okay, I'm going to look at a function v. V has a value at every one of these points because it's a function of the state x, just like here.
It's not necessarily the same as the x dot, right? It could be other function.
Oh yeah, it's not necessarily. It could be here. I could have had it. Okay. I could have had x dot is x or something, and then said x of x squared. Mm-hmm. I just for some reason x squared was, I guess, in my head, as is evident. So then, if you follow this, you could evaluate v of x here. You could evaluate v of x here. You could evaluate v of x at every single point in the solution of this differential equation that started from this initial point. Then you could say, okay, so v is changing with x. So how does it change with x as I follow this trajectory? So I'm not just interested in saying like, well, I look at v here and I look at it here. Like, because those are unrelated like points. In the trajectory, these are the points that come next. So you look at how does v change as I follow this trajectory. Is that clear so far? That's okay. And that's what this dv dt is. So if it's true that dv dt is always negative, what that means is that I started at some value of v, that since I wasn't at the origin, certainly because my function v of x has these properties, v of x was positive. Because I wasn't at the origin, I started somewhere. V of x is equal to, let me call this rho 1, which is greater than 0. So I start at some number, v of x at this initial condition is greater than 0, because I'm not at the origin. The only point where v of x is equal to 0 is the origin. All good? Okay. I want to make sure I don't lose anyone on this, because this is, like, super important for research. Then what happens is we say, okay, well, v dot is less than 0. So I follow this trajectory, and when I get here, so I make some amount of movement. Here, v of x is equal to rho 2, which is less than rho 1, which is greater than 0 still, because I'm not at the origin. But I know that I have decreased the value of v, because v dot is less than 0. If I follow this trajectory, v got lower. If this is true everywhere in D, that no matter where I started, if I follow the trajectory, V is always decreasing on that trajectory, except maybe not at the origin, for all x contained in D, but not including the origin necessarily, where V dot is less than 0. Then what this is telling me is that wherever I start, eventually, when I start with some positive v, it gets smaller and smaller and smaller and smaller and smaller. If it's always getting smaller, eventually it goes to 0. If it goes to 0, v of x is at the origin. So what that means is that then, essentially, if from all of these states in D, the only way that the system could behave is that the state goes to the origin from these points, that means I have asymptotic stability. Because I found a set of initial conditions where I said it's even a little more rigorous than this, but we'll have to do that in the proof. But you can see where this is going. You can see that that's basically like, because I didn't quite prove from any epsilon you can get any, or from any, for any epsilon there exists a delta. I didn't quite say all those things. You can see how this might lend itself toward that. And there is a rigorous proof that goes through and then in the end says like, here we can do this, we can do this. Then you can see it meets the definition of epsilon delta stability. We'll have to do that proof because that's super important to understanding this in great depth. But this is the genius of Lyapunov stability. Lyapunov was so smart to see this. It's so cool. He proves stability of a system in an epsilon delta sense, based on something completely unrelated to epsilon and delta, based on this completely different function that has special properties, where he said, well, if those hold and I can prove this other thing, then what I know is that the origin is asymptotically stable or whatever. It's so smart. It's so great. So from here, we're going to do an example. Oh, you have a question, Ricky?
Just trying to think further. Why Vx must be greater than 0 whenever the space D except in 0? Why this is a requirement?
Because so I need to make sure that the concept is holding true in my region here. So I think I'm gonna change up on the board in a minute the meaning of D. Okay. Pretend D means this region here, and pretend it's actually yeah. Okay, so we have this region D. So this region D is here. So in this region, if there are points where v of x is not greater than 0, where it's negative, then when v dot is less than 0, then from those points, I follow the trajectory and v gets more negative. But the only thing that I know about this function is that at the origin, x is equal to 0. So if it's going away from the origin, then I can't really say it's asymptotically stable. So the idea is, if you don't require this, the argument, like the whole conceptual argument, so the whole conceptual argument here is this. If I know that everywhere except at the origin, v of x is positive, but it's decreasing, but I know at the origin it's 0. If it decreases, 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 decreases forever and ever and ever, the only option you have is that you eventually decrease it to 0. If it was originally positive and everywhere it decreased, it must have decreased to 0 because it couldn't have gone lower than 0 without passing through 0. But when you hit 0, then you're at the origin, which is an equilibrium. So at the origin, once you hit that point, then then if you're at the origin, x dot is equal to 0. So if you start at the origin, you stay at the origin. So if you decrease to the origin, you don't leave the origin. But then that wouldn't hold if you could, well, it's possible someone could think of another condition, and I think that would be actually really cool in nonlinear systems theory if there were new ideas besides only Lyapunov stability, because basically all the nonlinear systems literature is based on this for the most part. But these arguments conceptually make that be the reasoning. If it's positive, then the only way it can go is decrease, and the only way it can go is decrease. It eventually decreases to 0. At 0, there's no further change. So that means that it was asymptotically stable.
I see.
Cool. Good question.
Can it work the other way? Like if v of x is less than 0 and then
I think it works.
dv dt is greater than 0?
Oh. That's an interesting question. So how would that go? So so it would be that v of x is, there is actually another paper that was talking about like barrier functions, and that one had some other conditions that also proved something about. I think it is hard for me to say right now without doing a rigorous proof, but I know that the direction you're thinking of, could there be other things that are similar but slightly different that give the same result? Yes, there are some. I'm hesitant to say more right here because I'm worried I'll not give all the conditions. But yes, that's also a really good thought. Some different ways of doing something like that exist. And you might be able to think of more. And maybe that can be a great invention of yours. The new ways of stability. You never know.
Maybe Kip, you can find a new property for the Lyapunov function.
That'd really be great. Can you do that, Kip? Let's have you do that.
No pressure, right?
5 more years, that's my expectation. Just kidding. Okay. So, I'm even debating if this is even helpful to do this one. I think this example is almost confusing. Sometimes, let me just do the summary of it. Sometimes people say the following. you can think of this Lyapunov function as representing energy. This is incredibly a confusing statement because it doesn't represent energy at all. It's mathematical. It's not at all related to physics. It's completely mathematical. Here's what people are saying when they're talking about this, to the best of what I've been able to tell they're trying to mean. The motivation, like in the textbook and stuff, before they talk about Lyapunov stability, so I gave it because I think that's a clearer understanding of like the very general, like, what are we talking about? It's very mathematical, and it says, like, if you have this function, you can kind of visualize how that would be true, because where else could it go? If it was decreasing, where else could it go except the origin? And when it gets to the origin, x dot is 0, so therefore it doesn't move. The way that, like, this gets derived in the book, so before they even talk about that, they just say, imagine we started think like, there are some things clearly lacking in what we can do so far. We said stability has these complex definitions, which it does, about epsilons and deltas. Then we said, one way we could actually have a checkable condition for those things, besides trying to figure out how we could, like, put epsilons and deltas in there, which for the most part is very intractable. Then you could, like, do a linearization. There's some cases where the linearization doesn't tell you, and it doesn't tell you global stuff. It only tells you local stuff. If you have eigenvalues that are 0, you don't make progress. You just say, I don't know, I can't tell from the linearization. So it leaves a lot to be lacking. So then you say, oh, how can I fill this gap? Wouldn't it be nice if I had other ways of proving whether or not a system was stable, and more than that, being able to prove global stability in certain cases, and being able to prove local stability when systems had 0 eigenvalues and things like this. Or instability in those cases. Well, I guess you can prove instability because then the eigenvalues would be... sometimes the eigenvalues might be positive, so sometimes you can still prove instability even if you have a 0 eigenvalue. If one of the other ones is positive, then you would just say, oh, it's still unstable. But say, like, all these things, you have somewhere the zero eigenvalues and negative eigenvalues. You say, I don't know if this is stable, unstable origin. So then it says, oh, okay, imagine the following. Imagine you have the following system. I don't remember all exactly where all these equations really come from in great details. This is supposed to be some pendulum with friction. I take the book's word for that. If you had asked me to derive the equations of a pendulum with friction, I don't really remember. I would have to look back at my physics book a little and look back at the force diagrams and be like, it's been a while. So just we'll just pretend this is true. Pretend that we look back at the physics book and that whatever the book said here is good. So then it says, like, oh, okay, so we're wondering about the stability of those 0, 0 and the pi 0 equilibrium points. So straight up, straight down. Now you can imagine that we have this energy here for the pendulum. It's the potential plus the kinetic energy. And if I knew enough physics to remember this, then here is the expression for that. Which, again, I am just taking the book at its word. I reviewed physics yesterday for another purpose, but at a rapid rate, and do not still remember how this comes about. But we'll also take this at the word of the book. If you remember how this comes about, let me know. But I don't. Some random uniform stuff. Here's your potential energy and your kinetic energy. That one looks like kinetic energy. I thought there should be, like, that could be kinetic. This one potential. Okay, I'm not quite sure. Okay, so then it says, oh, you know what? Like, when I look at this from a physical perspective at this system, I know there's things where, like, sometimes when the energy is positive, such and such a thing happens, or when the energy is 0, such and such a thing happens, and then they, like, kind of, basically the conclusion they draw is, you know what, I can tell a lot about the stability of the equilibrium by looking at this energy function. And then they say, oh, so now that motivates Lyapunov stability. And so, so now Lyapunov functions are kind of like energy, but they're not. That's like one example. It's so confusing to think of it that way. So they're not at all energy. It's just that one example happens to have a Lyapunov function that for this pendulum, it happens that the sum of the kinetic and the potential energy was like the Lyapunov function for this system was one that worked. So even if you see that in the books and stuff, or I think it's kind of confusing. Even on our slides, we say that for like the research talks. I also think that's super confusing. But like sometimes it's hard to be able to explain Lyapunov stability to large groups of people in a minute. To then be like, by the way, here's all the stuff you never learned about, and then I'm going to tell you all the advances that we just made in it. And so it gets kind of hard to like talk about research at all. So sometimes you have to use a simplification, even if you don't like them, just to try to make like an audience get something out of your talk in a short time. So anyway, because I know like I find it really hard a lot of times to follow the biological talks and stuff like that. So I think like everyone has talks when they're outside their area. Sometimes you have to just say something at some level, even if it's not 100%, or else people will not follow you for a whole hour. So here's the theorem about Lyapunov stability. I'm also going to introduce something that's just straight up notational stuff. So we're going to call dv dt is equal to the sum from I equals 1 to n of dv dx dxi times fi of x. So this is what you get as that dot product of dv, should probably do this, dv dx dx dt. So these are dotted. So then that would form something along the lines of dv over dx1 dot 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 dv over dxn times x1 dot x2 dot 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 xn dot. And so you can see how since x1 dot is equal to, so x1 dot is equal to f1 of x, x2 dot equals f2 of x, etc. So then you can see how when you multiply out these vectors, it becomes a big sum, which is what this is. And then we have that this means that v dot is a scalar, which is helpful to remember that even though it's coming from these vectors, ultimately it's their dot product. It's not a cross product or anything. It's a dot product. So it comes out as a scalar. So that means you can get what we say where we say v dot is negative. We mean that like strict negativity of a scalar. We don't mean like, oh, whether or not every entry in a vector is negative or something like that. We mean this was a scalar. Look at negativity of the scalar. There's one more notation I'm going to write up too. Then we also write this as equal to LFV. Again, this is purely notation. This is called a Lie derivative. I guess it might even be, because essentially the reason we do that is because it's dv dt is equal to dv dx. You can think of dx dt as being f of x, basically, because it's all the right hand sides make f. So x dot is equal to f of x. So that means that if I substitute x dot with f of x, I have that. So then people just do like straight up shorthand. They're just like LFV. So they move the thing that's on this side here, and then they put v. And then that means the derivative of this with respect to x times that thing. So I find it is a little confusing. People call this a more compact notation. I think it gets better over time. The more you see it, the less that it seems like, whoa, what is that? But, yeah. So that's the notation. Then I'll write the Lyapunov Stability Theorem. Okay, cool. So this is the Lyapunov Stability Theorem. So we have here let x equals 0 be an equilibrium point. Of x dot equals f of x, and let v map from some domain D to R. So the v is a scalar valued function because it maps from some vector x contained in the domain D to a scalar in the real numbers. We say v is contained in C1, so this means continuously I believe this is continuously differentiable, but does it have to be? Because v dot I think that's also confusing. Never mind, I'm not going to write this up here because I'm not 100% sure what I meant by that. But it's either differentiable or continuously differentiable within that domain because we're going to look at its derivatives. So whatever we do in the next part where we look at derivatives of v, those have to exist and stuff. So it has to be well-behaved derivatives for the following to hold. So if v of 0 is equal to 0, v of x is greater than 0 for all x contained in D but not including 0. If v dot of x is less than or equal to 0 for all x contained in D, then x equals 0 is stable in the epsilon delta sense. And if v dot of x is less than 0, so strictly less, for all x contained in D but not including 0, then x equals 0 is asymptotically stable. So it would have to be stable and attractive in these epsilon delta definitions. So several interesting things then come. So I guess these are several points about this. So the first thing is that this is what we call a sufficient result. Sufficient result. It says, if the following holds, then something. It doesn't say, if the first thing does not hold, then the second thing's not true. This is actually one of, I think, the hardest points about Lyapunov stability, is that the idea is you have to find a good V. So there's nothing that guarantees you that you make up some V in your head. So then, okay, one thing. How do you get this V? I don't know, you have to guess one. You just make it up. Try it, see, it didn't give me this, or it didn't. Oh, try another one. That's one of the things. So, Enrique knows a little more about this. Sorry, I should have moved these, Kip. Sorry, that was in the way. But,
it was okay, but thank you.
Yeah. But then, so, let me, I'm going to, again, say some general things about the research stuff that we do, and then kind of relate it to this, because this is super related to the research. So in my PhD, I worked I think almost every paper I wrote was about some type of what we call Lyapunov-Based model predictive control. This is a control design that in the controller uses Lyapunov functions and different things, and whether or not the Lyapunov function is decreasing and stuff like that, it uses that literally in the control design. So this is super applicable to the research. This control design, so we still work with that in our research group. It has benefits and disadvantages, and we're trying to see about overcoming some of the disadvantages over time. Benefits are, there's super rigorous proofs you can do in nonlinear systems that involve Lyapunov functions, so we can get really good provable properties for this controller under certain conditions. But the problem is these provable properties depend on that you can find certain functions that do certain things and mean certain things, and these are usually, it's not always easy to find those. Generally, if you use quadratic Lyapunov functions in real life, so things like x transpose px, so that would be quadratic, because if you actually multiply out the matrix multiplications, it turns out to have lots of squares of terms and stuff. So those tend to work well. This is really hard for industry to work with and scale that to a very, very large system, because you can imagine, so V has to be a function of all your states. Imagine that you have 1,000 states because you have a huge refinery. It's big. Then this just gets really hard to work with. So industry is not super into Lyapunov-based MPC, but it has really nice provable properties. So something that is in the current work